The Fairchild Republic A-10 Thunderbolt II carries a 30mm cannon so powerful that its recoil can visibly slow the aircraft mid-air when fired. That single detail tells you everything about what this machine was built to do. In a world focused on speed and stealth, the A-10 was designed to fly low, take hits, and keep fighting in the middle of chaos. It's meant to survive the battlefield and protect troops at all costs. This plane was built around a gun and designed to survive getting shot down. The Fairchild Republic A-10 Thunderbolt II carries a 30mm cannon so powerful that it can fire nearly 4,000 rounds per minute. And for a brief moment, the force of that firing can actually slow the aircraft in midair. That's not a side feature. That's the entire starting point of the design. Everything about the A-10 exists because of that weapon. At the center of the aircraft is the GAU-8A Avenger, a massive 7-barrel Gatling gun designed specifically to destroy armored vehicles. This is not a typical aircraft cannon used for air-to-air combat or light ground strafing. It was engineered during the Cold War with a very specific target in mind: Soviet tanks advancing across Europe. The expectation was not occasional use, but repeated sustained engagements against heavily armored formations. The gun itself is so large that it dominates the internal structure of the aircraft. It measures over 6 meters in length and weighs nearly 2 tons when fully loaded. The ammunition drum alone takes up a huge portion of the fuselage, holding over 1,100 rounds of 30mm depleted uranium or high explosive shells. This is not an aircraft carrying a gun. It's a gun with wings. To accommodate this, engineers had to design the aircraft around the weapon from the very beginning. The cannon is mounted along the aircraft's center line, slightly offset so that the firing barrel aligns perfectly with the nose gear. This ensures that when the gun fires, the recoil force is distributed straight through the aircraft's structure rather than pushing it off balance. Even with this alignment, the recoil is immense, producing thousands of pounds of force. In early testing, engineers had to ensure that the aircraft wouldn't stall or lose control during sustained firing bursts. The rate of fire is adjustable, but even at reduced settings, the destructive capability is extreme. Each round is capable of penetrating heavy armor, and when fired in bursts, the effect is devastating. The sound alone has become one of the most recognizable signatures of any aircraft in combat. But the real significance of the GAU-8 is not just its power. It defines how the A-10 fights. Unlike high-speed jets that rely on standoff weapons or precision-guided munitions from a distance, the A-10 operates up close. It flies low, engages directly, and remains in the combat zone longer than most aircraft would ever risk. The gun requires the pilot to point the entire aircraft at the target, committing to a direct attack run that exposes the plane to ground fire. This is where the philosophy of the aircraft begins to reveal itself. The A-10 was never meant to avoid danger. It was designed to enter it, survive it, and continue fighting. The presence of the GAU-8 forces the aircraft into that role, and everything else about the design supports that mission. In many modern aircraft, weapons are modular. They can be swapped, upgraded, or removed depending on the mission. In the A-10, the gun is not optional. It's permanent, central, and non-negotiable. Even as technology has advanced and precision-guided weapons have become dominant, the GAU-8 remains a core part of the aircraft's identity and effectiveness. However, this design decision reflects a very different approach to air warfare. Instead of prioritizing flexibility or technological dominance, the A-10 prioritizes reliability and direct impact. It's built to deliver force in the most immediate and tangible way possible, even if that means accepting higher risk, and that risk leads directly to the next major element of the aircraft's design. The Fairchild Republic A-10 Thunderbolt II was built with the assumption that it would be hit by enemy fire. Not possibly, not occasionally, but repeatedly. That assumption changes everything about how the aircraft is constructed, especially when it comes to protecting the pilot. At the center of that protection is what is commonly known as the titanium bathtub. This is not a nickname for marketing or exaggeration. It's a literal armored enclosure made of titanium plates that surround the cockpit, forming a protective shell around the pilot. The structure weighs several hundred kilograms and is designed to withstand direct hits from ground-based weapons, including armor-piercing rounds and shrapnel. Unlike traditional aircraft designs, where weight savings are prioritized to improve speed and maneuverability, the A-10 accepts additional weight as a necessary trade-off for survivability. The cockpit armor is not thin or symbolic. It's thick, reinforced, and carefully shaped to deflect incoming fire. The canopy itself is also hardened, providing resistance against impacts that would shatter standard aircraft glass. This design reflects the environment the A-10 was expected to operate in. Flying low and slow over a battlefield exposes the aircraft to a wide range of threats, including anti-aircraft artillery, small arms fire, and surface-to-air missiles. At these altitudes, even basic weapons can become dangerous. The titanium bathtub ensures that the pilot remains protected even when the aircraft is taking damage. To be fair, the placement of critical systems also follows the same logic. Wherever possible, essential components are either shielded, duplicated, or separated to reduce the likelihood of a single hit disabling the entire aircraft. The engines, for example, are mounted high on the fuselage and spaced apart. This positioning reduces the chance that a single strike or missile impact will take out both engines at once. The control systems are designed with redundancy in mind. The A-10 uses both hydraulic and mechanical backup systems, allowing the pilot to maintain control even if primary systems are damaged. In extreme cases where hydraulic power is completely lost, the aircraft can still be flown manually using what is known as manual reversion. This is not easy or comfortable, but it allows the pilot to maintain basic control and potentially return to base. Fuel systems are also protected and designed to minimize risk. The fuel tanks are self-sealing, meaning they can close themselves after being punctured to prevent leaks and reduce the chance of fire. Additional protective foam and separation between tanks further enhance survivability. All of these features come together to create an aircraft that is unusually resilient. It's not uncommon for A-10s to return from missions with significant damage, including missing sections of wings, damaged engines, or multiple holes from gunfire. In many cases, the aircraft remains flyable despite damage that would be catastrophic for other jets. The philosophy behind the Fairchild Republic A-10 Thunderbolt II goes even deeper when you consider how damage is expected, not avoided. Control cables are routed through multiple paths across the airframe, so even if one section is severed, others can continue functioning. The aircraft structure itself is built with load-bearing redundancy, meaning it can sustain structural damage and still hold together under stress. The landing gear is partially exposed even when retracted, allowing the aircraft to perform emergency landings without full deployment. This seemingly small detail dramatically increases the pilot's chances of survival if systems fail. The wings are also straight and thick, not for speed, but for stability and lift at low altitudes, where control and visibility matter more than velocity. Even the placement of the twin vertical stabilizers helps shield the engines from infrared-guided missiles by reducing heat visibility from below. Nothing is accidental. Every design choice reflects a single priority: bring the pilot home. The result is an aircraft that doesn't just survive damage, it's engineered to expect it, absorb it, and keep flying anyway. In a sense, the A-10 challenges the conventional idea of what a modern combat aircraft should be. It's not optimized for elegance or technological sophistication. It's optimized for endurance under stress, and this is where the defining idea of the aircraft becomes clear. It's not fast or pretty, but it refuses to die. The Fairchild Republic A-10 Thunderbolt II does not rely on a single system to stay alive. It assumes that systems will fail, and it is built so that failure does not mean the end of a mission. This is where its engineering becomes fundamentally different from most modern combat aircraft. At the core of this philosophy is redundancy. Critical systems are duplicated, separated, and protected so that a single point of failure does not bring the aircraft down. The flight control system is one of the clearest examples. The A-10 primarily operates using hydraulic systems to control its flight surfaces, but unlike many aircraft, it has two independent hydraulic systems running in parallel. These systems are physically separated within the aircraft so that damage to one does not automatically affect the other. If both hydraulic systems are lost, the aircraft does not become uncontrollable. Instead, it switches to a manual backup mode known as manual reversion. In this mode, the pilot directly controls the aircraft using mechanical linkages rather than powered assistance. It requires significantly more physical effort and reduces precision, but it allows the aircraft to remain airborne and, more importantly, to return home. This level of redundancy extends beyond flight controls. Electrical systems are also backed up, ensuring that essential avionics and communications systems can continue to function even after damage. The aircraft is designed so that power can be rerouted, maintaining critical operations even when parts of the system are compromised. The engines are another key example of this approach. The A-10 uses two turbofan engines mounted high and far apart on the fuselage. This spacing is not just for efficiency or maintenance convenience. It's a deliberate design choice to reduce the likelihood that a single missile or burst of gunfire will disable both engines at once. If one engine is lost, the aircraft can continue flying on the other, giving the pilot a chance to exit the combat zone and attempt a safe landing. The placement of these engines also reduces vulnerability from ground fire. By mounting them above the wings and shielding them with the aircraft's structure, engineers minimize exposure to direct hits from below, which is where most threats originate during low-altitude operations. Even the landing gear reflects this philosophy. The A-10 is capable of operating from rough or damaged runways, including improvised airstrips. The landing gear is rugged and partially exposed even when retracted, meaning that in an emergency landing scenario, the aircraft can touch down without fully deploying its gear and still maintain some level of stability. Weapon systems and targeting capabilities are also designed to remain functional under stress. The aircraft can carry a wide range of munitions, but it does not rely entirely on complex electronics to deliver them. The pilot retains the ability to engage targets visually and manually if necessary, ensuring that the aircraft can still perform its mission even if advanced systems are degraded. This layered redundancy creates a kind of operational resilience that is rare in modern aviation. While many advanced fighters rely on avoiding damage through stealth or speed, the A-10 prepares for the moment when those protections fail. It's built not just to survive damage, but to continue functioning through it. That distinction is important. Survival alone is not enough in combat. The aircraft must remain effective, capable of supporting ground forces and completing its objectives, even in degraded conditions. The A-10's redundant systems ensure that it can do exactly that. This is not efficient in the traditional sense. Every duplicated system, every separated component, and every backup mode adds weight and complexity. But in return, it gives the aircraft something that cannot be easily replicated: time. Time to stay in the fight, time to protect troops, and time to make it back home. And that brings us to the most defining characteristic of the A-10. The A-10 has a reputation that goes beyond its specs. It's known for something far more unusual: the ability to fly with severe damage that would destroy most other planes. This has been proven repeatedly in real combat situations. There are documented cases of A-10s returning to base with entire sections of their wings missing, with one engine completely destroyed, or with control surfaces heavily damaged. In some instances, pilots have landed aircraft that were barely recognizable after taking sustained fire. This capability is the direct result of everything built into the aircraft up to this point. The armored cockpit protects the pilot, the redundant systems keep the aircraft controllable, and the overall structure is designed to absorb and tolerate damage rather than fail catastrophically. The wings, for example, are straight and thick, providing both lift and structural strength. This design allows the aircraft to maintain stability even when parts of the wing are damaged. Unlike more delicate high-performance wing designs found on faster jets, the A-10's wings prioritize durability and low-speed handling. The tail structure is also designed with survivability in mind. The twin vertical stabilizers provide additional control and stability, especially if one is damaged. This redundancy in aerodynamic surfaces complements the redundancy in mechanical systems. One of the most important aspects of this design is how damage is managed rather than avoided. Instead of relying on a single optimized structure, the A-10 uses a more forgiving approach. Components are spaced apart, critical areas are reinforced, and non-essential parts are allowed to fail without bringing down the entire aircraft. This approach reflects a very different understanding of combat aviation. It accepts that in close air support missions, the aircraft will be exposed to continuous threats. Small arms fire, anti-aircraft guns, and even portable missile systems are all part of the environment. The A-10 does not try to eliminate these risks. Instead, it is built to endure them. The result is an aircraft that can continue flying even when heavily compromised. It may not perform at full capacity, and the pilot may have to rely on backup systems and manual control, but the aircraft remains operational. That alone can make the difference between survival and loss, both for the pilot and for the troops depending on air support. This durability also has a psychological impact. Pilots who fly the A-10 know that their aircraft is built to protect them in ways that most others are not. Ground troops, in return, recognize the sound and presence of the aircraft as a sign that support has arrived and will stay, even under fire. Overall, this aircraft prioritizes survivability and direct effectiveness over aesthetics and raw performance.